last lecture we had discussed some of the basics of
Yes, sir. We did capacitance.
electrostatics and capacitance. Okay, so let's continue from that point today. So before getting into current electricity, let's quickly discuss a little bit more about capacitance. So we had seen that capacitance, okay, so that is a electrical property of either a conducting object, okay, wherein if the object is like this, it's such that given a charge Q, it develops a potential V such that Q is equal to CV, where C is the capacitance. And we had seen that the value of the capacitance depends on the shape and size of the body. But of course, it has to be made of conducting material. So for example, for a spherical conductor, spherical metallic body, the value of capacitance is given by 4 pi epsilon naught into R, where epsilon naught was that permittivity of free space. So that constant 4 pi epsilon naught is related to the constant that we had seen in Coulomb's law and electrostatics earlier. Now let's look at the second type of definition of capacitance. So how we define capacitance? No, actually, Vedant, what happens now in the case of conductors, the density or any other material properties does not affect the value of capacitance. It is only the shape and the size, because it doesn't matter whether it is made of copper or steel or iron of a certain grade or whatever. The number of free electrons in a conductor is infinite. So the relationship between potential and charge only depends on, given the charge, how the charge is distributing on the surface. So it depends on the shape of the surface and the size of the surface of the conductor. So in that regard, no, it makes no difference what material the conductor is made of. It only makes a difference what is the shape and size of the conductor. So you will understand this in more depth when we discuss next year in more depth about electrostatics, why that happens. So here you just understand it as a factual thing. Okay, now the second thing is capacitance, defined for a type of device called a capacitor. You might have heard of capacitors. They are part of common, they're common components in electrical circuits, like you have a capacitor in a fan's regulator circuit, or you have a capacitor in a tube light circuitry, or in anything to do with a compressor like an air conditioner or a refrigerator, there will be capacitors. Capacitors are also there in electronic circuits on circuit boards which have printed circuit boards with ICs and all that, integrated circuits and semiconductor devices and all that. So there the capacitors are of much smaller size, for example, because they're on a circuit board. Anyway, so what does a capacitor do? Let's understand that first. Then we'll discuss about the capacitance. So a capacitor is basically a device. So a capacitor is a device which is used to store electrical energy. And by electrical energy, we actually mean potential energy of an electric field which exists inside the capacitor. So that's what we mean by electrical energy exactly. Anyhow, so it consists of, like, the simple design of a capacitor one of the simple primary designs is what we call a parallel plate capacitor. It consists of two metallic plates. So the geometry is more like two thin metallic plates like this, which are kept parallel to each other at a certain gap. Same size and all that, same surface area size. So suppose these are of surface of area E, and they are kept at a distance D. So the side view looks like this. So a parallel plate capacitor consists of two metallic plates placed parallelly to each other. Okay. Now, if we give the plates charge plus Q and minus Q, for reasons of induction, we will see that the charge accumulates on the inner surface of the plates, such that the negative and positive charge are facing each other, and that creates a uniform electric field. Remember, we discussed about electric field last time. So we had seen electric field lines were radially outwards in the case of a positively charged single particle. They were radially inwards towards the particle in the case of a negatively charged particle. And we had also understood the field lines due to a electric dipole. They all emanate from the positive charge and terminate at the negative charge. Now here what happens is that the field exists in the space. Okay, so given charges plus Q and minus Q each, okay, what happens? A uniform electric field, say E, exists in the region in between the plates. Okay. And this electric field is given by the formula Q upon epsilon naught E, where Q is the magnitude of charge given to each of the plates and A is the area bit of each of the plates. Okay. So this electric field produces a potential difference. So electric field existing between the two plates means that there's a potential difference between them. So producing a potential difference of V equal to Q into D upon epsilon naught E, or the magnitude of electric field into the distance. So this is the potential difference that is developed. So any capacitor, so this is the example of the parallel plate capacitor, but coming back to the general situation. So any capacitor has two plates such that if given charges plus Q and minus Q, okay, an electric field develops between the plates and produces a potential difference between the plates of V equal to Q by C, where C is again the capacitance. So now you can see in the case of the parallel plate capacitor, by comparing, you can see the value of the capacitance is epsilon naught A by D. Okay. So the larger the area of the plates, the more capacity they have of holding charge. And the lesser the distance between the plates, again, the more capacity they have of holding charge. Because if you invert this formula, you can see that Q is equal to CV. So if you're maintaining a potential difference of V across the plates, then the amount of charge that they'll be holding in the process, that is proportional to the capacitance of the system. So again, you can see from the formula for the parallel plate capacitor, the capacitance of the system is only a geometrical function. It depends on the area of the plates and the gap between the plates. It does not depend on, for example, what particular metal the plates are made of. They just need to be made of conducting materials. They can be made of copper, gold, silver, whatever. it will not affect the capacitance. What will affect the capacitance is the shape and the size. So the area and the distance between the plates. So this is how we define capacitance for a capacitor as opposed to capacitance for a single conductor. Again, the definition or the formula looks suspiciously same, that is Q is equal to CV. But in the case of a single conductor, Q was the charge given to that body and V was the potential developed by it, the absolute potential. In the case of a capacitor, Q is the magnitude of charge given to each of the plates. One of them is given positive and the other is given negative. And V is the potential difference between the plates, not the absolute potential. So that is the difference between the two. And additionally, it stores energy equal to half CV square or Q square by 2C. So this is the amount of energy that a capacitor stores. So very soon we will be looking at some applications of capacitors in circuits, electrical circuits. Like in class 9, 10th, you have studied about electrical circuits with resistors and cells or electrolytic cells or batteries. Now in this part, we will add capacitors to that mix. We will look at circuits which have resistor, capacitor and battery or cell or whatever. Okay, so let's look at a simple type of example of application of this now. So a parallel plate capacitor is typically represented by this kind of diagram, or in a simple circuit diagram, the circuit diagram symbol for any capacitor is just two sticks like this. Okay. So these are two wires attached to each of the plates. These are the plates. So this is the circuit symbol for a capacitor. Just like you know that this is the circuit symbol for a cell, for resistor, and this is the circuit symbol for a battery or a voltage source, which has something called EMF. So okay. Now coming to our particular example, a parallel plate capacitor of capacitance equal to 20 microfarads is connected across a battery of voltage 1.2 volts. Find the energy stored in the capacitor and the charge on each plate. Now, next what we'll do is, if the plates are separated to double the initial distance between them with the battery connected. So we are not disconnecting the battery while separating the plates. Then find the new charge and the new potential. Just a moment, people. Share this. So new charge and potential. Okay. On the other hand, if the plates are separated to double initial distance, but after disconnecting the battery, then find the new charge and potential. Okay, so we have the thing set up like this, that we have connected the capacitor across a voltage cell or a battery like this. So what will happen is that the capacitor's left plate will draw positive charge from the battery, the right plate will draw negative charge, such that now if this point is at a potential A and this point is at a potential B, the potential difference between the plates of a capacitor is given by the formula Q by C. And similarly, the potential difference between the plates A and B is equal to the potential of the battery also, because it's connected to the terminals of the battery, the points A and B. So by seeing these two, you can see that Q by C is equal to V. Okay, or the charge drawn by the capacitor's plates from the battery. When you connect a battery of voltage V, the charge drawn by each of the plates, now you substitute in this, so you'll see the charge will be 20 into 10 raised power minus 6 into the voltage, which is 1.2. So it is 24 into 10 raised power minus 6 coulombs, or what we can say is 24 microcoulombs. So this becomes the answer to the first part. Okay, that when we have connected a cell of voltage 1.2 volts like this across a capacitor which has a capacitance of 20 microfarad, then the charge on each of the plates will be this much and the potential. So that's the answer to the part A. Oh, sorry, to the part B. Okay. Q will be equal to 24 microcoulombs, and the energy stored in the capacitor, in addition to that,
Same as work done, right?
Slight difference. So I'll come to that also. So what happens is now in the process of sending the charge into the capacitor, there's also some dissipation of heat. So the work done by the cell is actually more than the energy stored in the capacitor. In fact, interestingly, it comes out to be double of the energy stored in the capacitor, and we'll see that calculation also. Okay, but currently let's just calculate the potential energy stored in the capacitor. So whether we write it like this or like this is one and the same thing. So in this case, it is half of 20 microfarad into 1.2 squared. So that is 10 raised by minus 5 into 1.44 joules. So we can say it is 14.4 microjoules. So this is the potential energy stored initially, like before we are making any change to the capacitor. So this potential energy will be 14.4 microjoules. Now the critical thing in this question actually, so this is the formula based part. Okay. Now we come to the critical part of this question, that how it's going to make a difference to the system whether we now pull the two plates apart while keeping the capacitor connected to the battery. So while these wires are connected, if we pull the capacitor plates apart, how the system will behave, versus if we break the connection, if we break the circuit and then pull the plates apart. So what difference is going to be in the two processes? Okay, that's what we are trying to learn through this question. So first of all, make sure that this calculation is clear with all the formula and all that. Okay, then we'll come to the C and D part.
I didn't understand the energy one.
Sorry, come again, beta.
Energy, formula of energy.
Half CV square. Okay. So V is the potential difference between the plates and C is the capacitance, right? So in SI unit, if I convert, it is 20 into 10 raised power minus 6 farads into 1.2 volts squared. So 1.2 squared will come out as 1.44, and this part is 10 raised power minus 5. Okay, so
Yes.
that's how I got it in microjoules.
So the
Okay, so let's understand this now. So what happens is, see, initially, so what actually changes about the system when we move the plates further apart is the fundamental property of capacitance changes, no? Because that's the property of the geometry. So this is D and the plate area is A. Originally, the capacitance was epsilon naught A by D. So that was 20 microfarad. Now, when I move the plates apart, the second time, what is happening is the capacitance is changing to epsilon naught A by 2D. It's becoming half. By increasing the distance, I'm compromising on the capacitance of the system. It cannot hold charge that efficiently. So the new capacitance, let's say this C prime, has become, sorry, this is 2D. So epsilon naught A by 2D. So it has become 2C or 40 microfarads. Okay. So that's the change to the system. Now let's see how we are making this change with respect to the battery. So initially we had this capacitance connected to the battery. So what had happened is it had drawn enough charge so that VA minus VB, which was Q by C, became equal to this potential difference.
so it will be half, right? Capacity.
Yeah, my mistake. It's become, I'm doubling the distance, not halving it. So this should be C by 2, so it should become 10 microfarad. Very good, that's correct. Okay. So यहाँ पे initially the charge was, we saw it was 24 microcoulombs. Okay, but now keeping the battery connected only, I'm changing the distance. So I'm changing the capacitance to 10 microfarad. So as a result, what will happen is that the potential difference between A and B will remain the same because that's connected to the battery. So the battery has that property of keeping this potential difference constant no matter what. So the amount of charge changes. This changes to Q prime. So Q prime becomes C prime into V. So it becomes 10 into 1.2 microcoulomb. So it reduces to 12 microcoulomb. So why it reduces to 12 microcoulomb is because when I'm switching from this to this, the part of the charge goes back to the battery from the capacitor. Instead of drawing further charge, the battery actually draws charge from the capacitor. Whereas if I had reduced the gap between the plates, then that would have happened. Suppose I had done this, that I reduce the gap between the plates to D by 2. So then the new capacitance would have become 2C. It would have become 40 microfarad. So now if I did this while keeping the battery connected, then the new value of charge in this would have become equal to 2 CV or 48 microcoulomb, whereas the voltage across the capacitor in each case is remaining the same because I've kept the battery connected. So that is a constant factor. The voltage is a constant factor, the charge is changing. Okay. But now if I do this, I've got this system first. Now I disconnect the battery. So in D part, I disconnect the battery. So the moment I'm doing that, I cannot change the charge on the capacitor. So this charge is now becoming fixed. This Q is equal to 24 microcoulomb. This is not getting disturbed. Okay. But what is changing is the capacitance. So next, keeping the battery disconnected in this way, if I move this to 2D, okay, so the new capacitance has become C by 2. So you'll see that the charge is the same. I have not disturbed the charge. But the voltage has changed now. The voltage across the capacitor has become so it has become 2.4 volts. So charge remained conserved, but capacitance changed. So potential changed. Whereas in the C case, I kept the potential constant because I kept the cell connected or the battery connected. So charge got disturbed, whereas the potential difference remained constant.
Sir,
Yes.
in the second one, can you tell me why the capacitance remains same?
In which one?
Third, sorry, D part.
D part. No, capacitance has changed, beta. Capacitance has gone from C to C by 2, na? But charge has remained conserved. Why? Because I've disconnected the battery.
Okay.
Understood, na?
Will it not lose its charge?
No, because it's not connected, na? So where the charge will go?
Okay,
It's
yes.
not connected to the battery anyway. So there's no conducting path for the charge to redistribute between the battery and the capacitor. Got it, no?
Yes, sir.
So this question kind of also helps us understand the function of a cell or a battery or any what we call DC voltage source, which maintains a constant potential difference. Okay. So a DC voltage source. Sometimes it is called a cell or it is called a battery. Actually, a battery is a collection of more than one cell. And a cell is a single unit like an electrolytic cell or a photochemical cell or whatever device which makes use of some kind of chemical reaction or some chemical property of a system to maintain a constant potential difference. Okay. So basically, a cell consists of kind of a structure which has two what is called electrodes, which are metallic rods. So these electrodes maintain because of some kind of chemical reaction happening inside the cell. These are maintained at a constant potential difference. So a chemical reaction, like for example electrolysis, maintains a constant potential difference between the electrodes, which are basically like metallic rods A and B. And this potential difference V, it is called the terminal voltage across the cell's electrodes. In fact, the one having positive potential is called the cathode and the one having negative potential is called the anode. Okay, but that's not important for us over here. So the important thing is the terminology. One is that there is something called terminal voltage. So that terminal voltage is the potential difference between the terminals. So this is like an inbuilt property of the cell. Okay. Now there is another term called EMF or electromotive force. So this name is very confusing because it seems like a force, but actually it's not a force. It is something to do with work done by the internal force. So what happens is that when we connect the cell or the electrodes externally through a circuit, like we've taken some conducting wires and there's some kind of a device, let's say, which is consuming electricity, and the other wire is connected to the negative terminal. So these are the electrodes A and B. So what happens is that in this situation, continuously, because A and B are at a potential difference, we say that conventional current is flowing from A to B because A is at higher potential than B. Actually, what is happening? Electrons are flowing in the reverse direction. Okay, because now we know, like at the time when electricity was discovered, electrons had not been discovered then. So we didn't know that there's actually electrons which are negatively charged particles which go from lower to higher potential. So we just thought that there's some kind of positive charge that flows from A to B. But later, of course, we understand that positive charge is located with the protons, which are embedded in the nuclei with very strong binding energy. So it's not really possible to bring them out. It is the electrons which are in the outermost shells of metallic or conducting kind of elements. Those electrons are kind of free to move about within the lattice of the metal. They are not bound to the nuclei. They are bound to the metal itself, but they are not bound to the nuclei. So they are kind of free to travel under the influence of electric field or potential difference. So what this does is that connecting the two electrodes by a circuit consisting of an electrical wire in continuation, because even the device is conducting. So there is a path for current to flow between the higher potential electrode and the negative potential, lower potential electrode B, A and B. So continuously there's a stream of so-called electricity or electric current that flows from A to B. Actually, there's a stream of electrons that flow in the opposite direction from B to A. But as they flow from B to A, the excess electrons that are accumulated at A, they again flow back to B through the electrolytic cells process. So what happens is that the internal chemical reaction that is happening inside the cell, that is making electrons continuously go back from from A to B, and the external circuit is carrying those electrons from B to A. So this process is continuously taking place. Okay. Of course, for it to take place continuously, some energy is expended by the cell. So the cell eventually gets discharged. But as long as the chemicals in the cell have not got depleted, they still have a reserve of chemical potential energy. It's going to maintain the potential difference across AB. And as long as that potential difference is maintained, if there's an external path or a so-called circuit by which the electrons can flow from B to A, electrons will flow. Okay, and that process will continue. So in that process, the electromotive force is defined as the work done per unit charge, okay, by the cell to transfer charge across its electrodes. So EMF is given by the symbol capital E, or sometimes you also write it as EMF. So EMF or E is equal to the work done per unit charge by the cell or by the internal forces of the cell. Okay. So you can understand that EMF is also expressed in volts, because as we have defined, the unit of work done divided by charge is joule per coulomb, which is the same thing as volts. Just a minute, people. I will restart this program. Yes, Yashovardhan, that's correct. In household power supply or even in industrial power supply, for that matter, there is alternating current which is used, which is through a different mechanism. That happens through the mechanism of electromagnetic induction, and not through something like a electrolytic cell, which is maintaining constant potential difference. Okay, but this is the kind of electricity that is provided by, let's say, your like your lithium ion battery, which is used for powering most devices like tabs or mobile phones, or even the regular pencil batteries and those kind of things that you have seen for devices like torches, radios, things like that, transistor sets. So that kind of circuitry we are talking about. So work done in joules per unit charge in coulombs, it becomes, okay, so 1 volt is equal to 1 joule per coulomb. The reason why AC is used in household is because the power generation that is happening at that scale for household power supply or industrial power supply, it is more efficient through processes which generate alternating current, like for example thermal power plants or nuclear power plants or hydroelectricity. Okay, so those processes all involve electromagnetic induction, and electromagnetic induction process used for generating electricity always generates an alternating voltage. Okay, whereas the process of storing charge in an electrolytic cell and then using that as a battery, that is more that is less efficient, that's less energy efficient. So if we needed to have giant electrolytic cells to power our household supplies and all that, it would be a much more energy inefficient process. It would be more expensive, it would be more difficult on the environment, everything. So that's why that doesn't happen. Okay. It is merely a method of power generation, the way it is done. So alternating current becomes the current that is delivered in that kind of scale. So anyway, alternating current is a different topic. Okay, we will discuss about that later. So here sticking to DC voltage sources. Okay, so you can see that the quantity EMF seems to have the same unit as terminal voltage. Okay, so terminal voltage is also in volts. No? So there's a connection between the two, and let's understand the connection between the two now. So the relationship between terminal voltage and EMF E. Let's understand this next. Okay, for a given cell. So if we have an ideal cell, and we'll discuss about what we mean by ideal. For an ideal cell or voltage source, if we connect a resistor across the cell, you know the circuit symbol for cell is this, we had discussed this a while back. So if it has EMF E and we connect an external resistor across it, so what happens is that the terminals of the battery are, let's say, A and B, these. So if the current going through this is I, then by what you know as Ohm's law, the potential difference across the resistor VA minus VB should be equal to the current into the resistance. But here you can also see the potential difference, which is basically terminal voltage for the cell. This becomes equal to EMF for an ideal cell. Because an ideal cell does not have any internal resistance. That is a property of an ideal cell. So comparing these two equations, you can see that E is equal to IR. So the current drawn by the resistor connected to that cell will be E by R, where E is the EMF and R is the resistance. But this is occurring, the terminal voltage is equal to the EMF in this case because an ideal cell has zero, nothing is perfectly zero, but basically it's negligible internal resistance. However, a real cell will have a slightly different potential difference because it has something called internal resistance. So for a real cell, if we connect across this, what we will observe is that the current drawn by the resistor and the terminal voltage across the battery are slightly less than expected. I is less than E by R. And the terminal voltage, that is the voltage difference between the electrodes, that is also less than E. So why this happens? This happens because the cell has a non-zero internal resistance. Which we generally denote with a simple R. So because of the internal resistance, the effective situation, the effective circuit diagram for this kind of a cell, for which we cannot ignore the internal resistance, the effective the circuit diagram becomes like this, that along with the external resistor which we have connected across the terminals. Okay, so let's say these are the terminals of the battery, but along with that, the battery internally also has some resistance, which is called the internal resistance. So the potential difference across AB, this is the terminal voltage. And now you can see because of that internal resistance, it is not the same as the EMF. If a current I is going through this, you can see I over here becomes E upon R plus R. You can see that the actual I is less than the expected I. because of the presence of internal resistance. So this is the actual current, and this is in ideal case what the current would have been if the internal resistance was 0. And that is why in that circuit now you can see that the terminal voltage, which is the voltage difference between A and B, that is equal to I into capital R. So if you substitute the value of I from there, you can see the terminal voltage becomes the X. So this is the current. Or another way to understand the terminal voltage is E minus I into small I. So the presence of the internal resistance reduces the terminal voltage. This would be the terminal voltage in ideal case. But this is the real case. It is less than this.
Can you scroll up?
Yeah, that's good.
Can you scroll down? So bad. So can you scroll down? Can you scroll down?
Okay, so we will discuss this with some numerical examples and it will become more clear. The difference between terminal voltage and EMF, okay, of an electrolytic cell, and how internal resistance plays a role in that terminal voltage idea. Okay. So I realize some of these terms will be new for you people and we are doing it like fast track. But that is the nature of this KVPY preparation thing, that we cannot get into the depth of these chapters. But at the same time, we have to know some of the key terms and all this. We just understand them as definitions and formulae, and we learn how to apply them in certain situations. And then when we come to class 12, then we do these chapters in full depth. You will see that this will help you a lot there also. Okay, so let's understand a typical question, numerical problem, to understand this application. So we have the same circuit, but in three different situations. This is a switch which has been kept in closed condition. Now this has an EMF which is of, let's say, 20 volts and an internal resistance which is of 2 ohms. And this external resistor is 198 ohms. Okay. And this switch is closed. So this is the current I flowing through this. Okay. Now in the second case, we got a combination of two resistors. And this battery here has an EMF of 50 volts and an internal resistance of 3 ohms. And again, this switch is closed, so current I is flowing through this. Now, in the third case, then we have this 20-volt battery with an internal resistance of 2 ohms. But this time we've left the switch open. The switch is in open condition. So in each circuit, find current I, okay, terminal voltage across the cell. Let's say VT. And the resistance, sorry, the voltage across each of the resistors. So for each of the corresponding circuit diagrams, say diagram 1, diagram 2, and diagram 3, You have to calculate each of these three things: current, terminal voltage, and the voltage across each resistor. So for example, in the second circuit, there are two resistors. So separately, you have to mention the voltage across each of these resistors.
Can you scroll up just for the real cell part?
Yeah,
Because
I'll scroll up.
for 1 second. So,
Okay, so let's come back to the question. Yes, I have received a couple of answers. Just verify it. Yeah, Vedant answer is correct. Oh, sorry, just a moment. I have given you a wrong value in the second question. R2 is 79. Okay, just make it. I mean, it's okay. 89 is also fine, but we'll just get a very odd value. 79 ohms.
So what the value of E in the second part?
E is 50 volts, 50, and internal resistance is 3 ohms. Okay.
so terminal voltage in a
Yes.
will be ER by R plus R. You've given it as
ER by
ER
R plus R.
for real case.
In each of these cases, like terminal
So
voltage
why
is
did
equal
you give
to.
it as like E minus 1 by R? 1 into R. I into R.
No, not 1 into R. It is, see, this thing,
I.
this terminal voltage, which is I into capital R. This is the same thing as actually E minus I into small r.
Okay.
This is how it's becoming this one. It's the same thing as E minus I. Because you have this relation that I is E divided by R plus R.
Yes.
Clear now? No?
Yes.
Okay, so in the first case, you will get your current as E divided by R plus R. So that is 20 divided by 200. So that is 0.1 amperes. Okay. So you will get the terminal voltage. You can write as this
19.
or whichever you like. Okay, so you can see 19.8 volts. So you can see that the terminal voltage is less than the EMF by a certain amount, and that certain amount is small I into small r. And we'll get the voltage across the resistor as I capital R. So that will be same thing as the terminal voltage, 19.8 volts. So these two, the terminal voltage is equal to the voltage across the resistor, which you can write as VA minus VB. We just show these 2 points as the terminals. But in the second case, if these 2 points are the terminals of the battery, then in between there's another point between the resistors. So you'll have to take that into account for calculation. Okay, so in the second part, you can take the net external resistance as the series combination of R1 plus R2. So that is becoming how much now? 118 plus 79. So that is 3 short of 197. Okay. So the current in the circuit will become this. So that is 50 divided by 197 plus 3. So 0.25 amperes. So now you can see that the terminal voltage across the battery is E minus IR, or that's the same thing as I capital R. So terminal voltage will come out to be this much. And the voltage across the first resistor, IR1, that is the potential difference between these 2 points, VA minus VC basically. So that will come out to be R1 was how much now? 118. So 1/4 of 118. And the potential difference across the second resistor, that is VC minus VB. So that is again, second resistor was 79 volts. So divided by 4.
Seven five.
So you can see in this case what is happening, V1 plus V2, that is equal to the terminal voltage, because this is VA minus VC and this is VC minus VB. That is equal to the terminal voltage, which is VA minus VB. That's how Ohm's law is working out in that particular circuit. And the third circuit is just to test your very fundamental concept. The circuit is broken, so there is no current. Okay. In the third circuit, the current will be 0. So the current is 0. You can see the voltage across the resistor will be 0. Okay. So the terminal voltage across the battery will be equal to the EMF, 20 volts. So that is why sometimes as a statement we say that EMF is equal to open circuit terminal voltage. Open circuit means when we have kept the circuit open, it's not a closed circuit. So we are not drawing any current from the battery. So in the open circuit condition, the voltage across the terminals is equal to the EMF of the battery. It's the same thing as the EMF. But the
But
moment the
then
circuit,
the
yeah,
I into external resistance won't apply, right?
no, it will not apply here because the circuit is broken, na, beta. So basically what is happening here is if you take the point, these 2 points as let's say C and D, and the terminals of the batteries are A and B, these 2 points, you can see that between C and D, there is no potential difference that is applied because the circuit is broken at this point. So there is no current through the resistor.
Yes.
Understood? No? Because VC minus VD is 0 here. No? So the resistor, okay, so that's why the current is becoming 0. Okay, so hope this is clear. Now next up, we will learn how to do some power calculations in a circuit. Okay, so if we have a current I going through a resistor, so then basically if the resistor is connected between these 2 points, we know that the potential difference between these 2 points is equal to IR. So we know that if dq charge flows from A to B, by definition of potential difference, which we had seen earlier, the energy dissipated will be the charge going into the potential difference. Okay, so it will be dq into IR. This is the energy dissipated when charge dq is going across that potential difference. Okay. For charge dq going from A to B. So in time dt, if this charge flows across from A to B in time dt, then the power dissipated, that is the rate at which energy is dissipated at the resistor, that power P becomes the rate at which this energy is getting dissipated. So it becomes dq by dt into IR. And dq by dt is nothing but the electric current. It's the rate at which current is flowing. So that's why we say that the rate of power consumption or the rate of power dissipation by a resistor, so rate of energy dissipation by a resistor, so this one together, or power consumed by the resistor. So for example, if we say that there is a resistance of 200 ohms and we pass a current of 5 amperes through it, we want to find first of all rate of energy dissipation. And now secondly, we say that let's say 10% of energy dissipated or consumed, whatever, is converted to light. Because the resistor is glowing, let's say, because of the heat dissipation is converted to light. So find the power that is in watts of light emitted. So we'll just use this concept over here. We'll see that by this formula, the power consumed by the resistor, that is I square R. So that will become 5 square into 200 in watts. So 25 into 200. So that will become 5 kilowatts. Right? No, 50 kilowatts. No, 5 kilowatts. And now 10% of this is should be 0.5 kilowatts. So simple thing like this. So this is the use of this formula. Okay, now the next part we'll see in understanding energy calculation in a circuit is power supplied by a voltage source, basically a cell or battery, whatever. So we are talking about an ideal cell. Then it has no internal resistance. If its EMF is E and you are drawing a current I from it, then power supplied by the cell just becomes E into I. Okay. Whereas if you're talking about a real cell, so it has some internal resistance also. So if you're drawing a current I from it, then the power supplied by the cell will actually be equal to terminal voltage into I. So it will become EI minus I square small r, because terminal voltage is into I. So now, for example, if we have a situation like this, we have two resistors of 18 ohms each, and that is connected to a cell which is having an EMF of 10 volts and an internal resistance of 4 ohms. Now we want to calculate the power consumed by each resistor and the power supplied by the source, that is the cell. Now of this power, how much power is generated in the cell's internal process, okay, and how much is dissipated within the cell. So we'll understand what that means also. So let's try this out. Then we'll also see an example with parallel combination of resistance. This is the so-called series combination of resistance. So one more thing we will see is the total energy in a certain amount of time. So we'll add that. We're doing this, and find the total say energy dissipated by both resistors A and B in a time of, let's say, 10 seconds. Whereas the total energy generated by the cell in the same amount of time. So you'll see the answer to the fourth part should be greater than the answer to the third part, because some amount of the energy generated by the cell is getting dissipated internally within the cell. How we know that? Because the cell has internal resistance. Only if it had been an ideal cell, then that would not have been happening. Whatever energy is generated by the cell, it would have been available to the two resistors A and B. But now in the case of a real cell, less than that energy is available to the two resistors outside, because it has internal resistance. So the cell itself is dissipating some of the energy that it generates. So to understand here, there's a difference between the term power supplied by the source and the power generated by the source. Power supplied by the source is how much power is supplied by the cell, which is available to A and B, the two resistors that are connected from outside. Whereas power generated by the cell is that by the internal process, the generation of the electromotive force, which is pushing the electrons. So that force is doing certain work. So how much energy or what rate at which that energy is being generated by the cell. A part of that energy is getting dissipated within its internal resistance, whereas part of it is available to the circuit outside. So that is the difference between the power supplied and the power generated by the cell. Okay, so let's, yeah, I'll just verify the answers for Vedant and everybody else also. So hope everybody else has also more or less solved this question by now. Anybody else got the answers? Aparna, Ibrahim, Raghu, anyone else? Om, Pratyush. Okay, so let's start the whole problem by understanding the current in the circuit. So remember, there's an internal resistance. Okay. So sometimes, people just find it more convenient to say that this is equivalent to just treat the internal resistance like another resistor. Just helps to visualize the circuit. But then this whole thing is your cell. The internal resistance is within the cell. This is your cell. And these are the terminals of your cell. So we'll treat the terminal voltage as the voltage across this. Just becomes easier to visualize this. So whether you go with the original circuit diagram or an equivalent circuit diagram, where you are showing the internal resistance separately, you realize that the current is, in this case, given by this. So that will become how much now? That will become 10 volts divided by 40 ohms. So 0.25. amperes. So now you can see that this is resistor A, this is resistor B. The power consumed by resistor A will be equal to the power consumed by the resistor B, which will be equal to I square R. So 0.25 whole square into, they were 18 ohms each, right? So that is 1 by 16 into 18. That is 9 by 1.125 watts
Yes.
each. Okay. Now you can also see that the power supplied by the source, that only has to be PA plus PB logically also, and you can
Yes.
understand that that is basically also equal to terminal voltage into I, or E into I minus I square small r.
2.25.
Yeah, so whichever way we calculate, you can see that this is going to be 2.25 watts. Okay. But the important thing is that the power generated by the source through the internal process, that is E into I. So that is going to be 10 volts into the current. The current is how much? 0.25. So you can see that is more. So so the power generated by the source, that is in fact 2.5 watts. But ultimately the power supplied is less than that because some of it is getting dissipated by the internal resistance. So this difference you can see is the power dissipated within the source or within the cell. So that's basically I square small r, which if you work out will come out to be 0.25 watts. Okay, now the next question I want to do will be in a slightly different format. Okay, it will be, instead of giving the resistances, I will give you what is called the rating of 2 or 3 bulbs or whatever. So you'll notice that on electrical devices, there is something called a rating, which is always given in terms of wattage versus voltage. So for example, we can have a bulb rated as 100 watts slash 50 volts. So what this means, this statement that the rating is so much, what this means is that when connected across a potential difference of 50 volts, okay, the bulb, which is basically acting like a resistance, will consume 100 watts. This is the meaning of the statement. Okay. So whenever you see a question with this kind of thing given, you understand that indirectly what is happening, that the bulb is basically like a resistor, such that if you have connected this resistor across a potential difference of 50 volts, then it should draw current in such a way that the power it consumes, that is I square R, that should be equal to 100 watts. That is the meaning of this. Okay. So now you can see that basically 100 watts, which is the power, will be equal to this potential difference divided by R whole square into R, I square R, this statement. So basically it's equal to 50 square divided by R is equal to 100. So this is telling me indirectly that the resistance is how much? It is equal to 50 square divided by 100. That is 25 ohms. So this whole statement, this rating, okay, it means this. Okay. So the rating of 50 volts slash 100 watts, it means that the resistance is equal to this power. So it is equal to the voltage square divided by the power. In this case. Okay. So this is the meaning of rating. Okay. So now the thing is, you might see questions of this type. So how to handle these questions, that's the thing we have to learn. So now what is happening? We have 4 identical bulbs of rating, let us say 100 watts, 25 volts. Now they are connected in parallel across a cell, or let's say across an ideal cell. Of EMF equal to 12.5 volts. Find the power consumed by each and the power supplied by the cell. You can see the question is indirect because you're not given the resistance of the bulbs, but you're given some idea about how to connect them in a circuit. You're given the EMF of the cell, you're given that internal resistance is zero because it's an ideal cell. Or even if the question doesn't mention it's an ideal cell, but just the fact that it does not give internal resistance. If only the data about EMF is given, then you have to assume that the internal resistance is zero. Okay, so what I also want to show you here is how to do a question like this in the most efficient way. I'm sure all of you can do it numerically by finding the resistance, then drawing the circuit, then finding the net resistance and all that. But how we can do this more efficiently, let's understand. So let's start with understanding the rating that is given. Okay, so if I have a single bulb has a certain resistance, and if I connect it to the given rated voltage, so the given rated voltage was 25 volts, right? What happened is it consumed a power of 100. Wasn't it 100 or whatever? Yeah. So it consumed 100 watts. When connected in this way. So it drew a current in such a way that okay, for this case, you can see whatever the current was, I square R is equal to 100 watts. Okay. Now from this, I'm taking 4 of these bulbs, connecting them in parallel. So each of them have got the same resistance as in that circuit. Okay. And then I'm connecting this combination across a battery, but that has a different voltage. It has a voltage which is 25 by 2 or 12.5 volts. So what will happen is that across these 2 points now, here across these 2 points, the potential difference was 25. But now across these two, the potential difference has become 12.5 volts. So the current in each of these, in comparison to that one, will become how much? Half the voltage, so become I by 2. And the total current here will become I by 2 plus I by 2 plus I by 2 plus I by 2, so 2I. So you can see that the power in each bulb will become I by 2 whole square into R. So in comparison to this, you can see it's 1/4. Okay. So it will be 25 watts each. Okay. And here, the power supplied by the source, that will be equal to 2I into V prime. So that is becoming so I into V, so 100 watts. Okay, and that makes sense also because the power supplied must be equal to the total power consumed by all the bulbs put together. So each bulb is consuming 25 watts. So this must be like this. Okay. But let's see a different example. Suppose I take these 4 bulbs and now they are connected in this way. I connect them like this now. And this time, let's say I use the same voltage of 25 volts. Okay. Now, again, there's a different part of the question. So now, again, calculate power consumed by each. And the power supplied by the source. So use this data only. These are the bulbs that we are, each bulb has that same rating. 100 watts slash 25 volts circuit. But now we've connected like this, that 2 of them are connected in parallel, and that combination is connected with 2 other bulbs in series. And the whole thing is connected across a line which is having an ideal cell with EMF of 25 volts connected. So in this case now, how much each of the bulbs will be consuming and what is the total power supplied by the source? Okay, so again, if you're talking about how to solve a problem like this most efficiently, okay, so without doing that much calculation. So you can see that this combination is basically R by 2. So the whole circuit is having an equivalent resistance of R by 2 plus 2R. So 5R by 2. Because this combination is a series combination having equivalent resistance 2R. Okay. So now if I take this current as I prime, that current is going into these two. And also you'll see that by symmetry, this and this are the same. So I double prime will be half of I prime. Now this I prime will be equal to how much? It will be equal to this voltage divided by equivalent resistance. Okay. So the voltage is the same as the simple circuit that we had seen earlier. So if you compare these two circuits now, you can see the voltage is the same, but the resistance has become 2.5 times. So the current will become 1 upon 2.5 times. Okay. Voltage is the same as above, 25 volts. Okay. If you compare this and this circuit, you can see the voltage is the same, but the equivalent resistance has become 2.5 times. So the current I prime should be 1 upon 2 and so it should be 2 by 5 I or 0.4 times I. Okay. So now you can see that the power supplied by the source is V into I prime. So that will become 0.4 times what it should have been here, which is 100 watts. So the source is managing to supply only 40 watts of power because I've connected it to a much larger load. No? I've increased the load by a factor. The external resistance is called the load. So I've increased the load by a factor of 2.5. So the current has reduced by a factor of 2.5. So the source is not able to
2.5, you mean then it would
1
be
upon 2.5. So that's why it's becoming 0.4 times. The resistance has become 2.5 times, right? So the current will reduce by a factor of 2.5 times. So it's become 0.4 times. Okay. Now let's call these resistors A, B, C, and D. So you can see that the power consumed by A is equal to the power consumed by B. That is equal to I double prime square times R. So I double prime is half of I prime. So it is 0.2 I whole square times R. So it is 0.04 times I square R. So it's going to be 0.04 into 100. So each of these is consuming only 4 watts. And the power consumed by C is equal to the power consumed by D. And that's equal to I prime square times R. So that is 0.4 I square times R. So that is 0.16 I square R. So that is 16 watts each. So now you can see that 2 of these are consuming 16 each, so 32, and 2 of these are 4 each, so that's 8. So 32 plus 8, 40 watts, it's accounted for, the total power supplied.
So
So can you explain how you got I prime as 2 by 5?
That calculation is here, beta. See the equivalent resistance of the circuit, na, R equivalent, is becoming 5 by 2 R. Na? This, okay. So next step, how much is I prime? Is this voltage divided by equivalent resistance?
Yes, sir.
Now that equivalent, so this thing is further becoming V divided by 5 by 2R. Okay, and I in the earlier circuit we had seen was V by R. So it is 2 by 5.
Yes.
So if you compare this combination circuit with a simple circuit of a single bulb connected across the standard voltage source, you can see that what the combination has done is it's increased the resistance from R to 2.5 times R, but kept the voltage of the source the same. So the current drawn is becoming less, no, by a factor of 2.5.
So,
Yes.
sir, in the circuit, we are taking I prime. So, what is I?
See, that is the comparison. No? This is the circuit with a combination of resistance, whereas I was the standard circuit with only one bulb, which express the rating of the bulbs. See this diagram above now.
Yeah, sir.
Understood the situation?
Yeah, sir, got it.
So if any one of these bulbs I connected across the standard voltage, then that circuit would have a current I. So when I'm now using this combination circuit, that combination is drawing how much current from the voltage source is drawing I prime instead of I, because the whole resistance of the circuit has changed. Right?
Yeah, sir.
Okay, so these kind of calculation, simple type of calculations, but based on concepts of energetics as well as equivalent resistance, like series and combination and all that, series and parallel combination, as you can see, and also the inclusion of internal resistance concept. Is all this put together is all about our current electricity type of thing. Okay, now I know that we are almost out of time, but I just want to do a brief introduction into magnetics today so that you can get started with some of those formulae. And next time we can look at more numerical type of applications. So magnetism. So just like electrostatics was the interaction between stationary charge, static charge, hence the term electrostatic. Okay. Now the term magnetism actually is more from magnets which were naturally occurring materials. And for a long time in physics, we did not understand how exactly magnetism is generated. We just thought that, okay, there are naturally occurring materials which have a magnetic property, which have the ability of affecting current, or it has the ability of affecting other magnets and all that. But later, of course, with the experiments by Oersted and other people in magnetism, it was understood that magnetism is basically to do with the interaction between moving charges. So even when we don't have a current carrying conductor displaying magnetism, even when we have a solid magnet, a naturally occurring solid magnet or an electromagnet or whatever, showing magnetism, so there is no visible current inside it as such, but actually what is happening, it is the orbital motion of electrons in within the atoms. That orbital motion is actually causing the magnetism. So what is behind magnetism? It is always moving charge. So magnetism is the interaction at a fundamental level between charges in motion. So if we are thinking about magnetism generated by a bar magnet or a horseshoe magnet or something like that, this might seem a little strange because, macroscopically when we observe that, we don't think that there's any moving charge because there's no current or anything. But when we look at it microscopically, it is somehow that the orbital motion of the electrons are all linked together in such a way in such materials that they create the natural effect, or they create the equivalent effect of charge in a sort of circulating motion, just like you would have in a solenoid, okay, which is like a circular coil carrying current. Okay, so we'll understand that connection as we go along, but here we will start by understanding magnetic field. So we'll go in the reverse order over here. In electrostatics, we first understood about force. Then we understood that field is the medium of force. That is, charge creates electric field and electric field affects another charge. So that is how charge Q1 is interacting with charge Q2. That Q1 is creating its own field, and then Q2 being present in that field is interacting with that field and it experiences a force. Or likewise, Q2 is creating its own field and that field is interacting with Q1 and that's creating the reaction force on Q1. So that's how we understood electrostatics from a basic level. Now in magnetism, we go in a slightly reverse order. What we say is that, okay, let's assume by some natural effect like the presence of a bar magnet or whatever, we have magnetic field, okay, which we denote with the symbol capital B. It's a vector field. So how does this magnetic field influence a charge particle? So we understand the effect of magnetic field on a moving charge first. We don't at this stage, we are not worried about what is creating the magnetic field. Let's say the magnetic field is present for us ready-made. Like many of you would have heard and know that Earth has its own magnetic field. Okay, so let's assume we are doing the experiment related to the Earth's magnetic field. So how if we have a moving charge in the Earth's magnetic field or in the presence of the Earth magnetic field, how it will interact with that moving charge. So let's understand that first. Okay. So there is the fundamental formula which is for magnetic force acting on a charged particle. Let's say its charge is Q and its mass is M, moving. So the charged particle should be in motion. If it's at rest, it will not experience force. So moving with, let's say, velocity v inside a magnetic field. This magnetic field is given by the vector capital T. So this force, it is sometimes called Lorentz force, but otherwise we call it just magnetic force. It is given by this simple formula, Q into V's cross product with V. This is one important fundamental formula we have to understand. Okay. So here it's a cross product, so it's a vector quantity. Okay. So in this, first of all, we'll understand that Q is with sign. Okay, so therefore, positive charge experiences force along V cross V, and negative charge in the opposite direction that experiences force along minus of V cross V, because Q is a scalar quantity which will have plus or minus sign. So accordingly, the vector F will have plus or minus of a scalar into V cross V. That's one thing to understand. The other thing to understand is the property of cross product, that magnitude of this will become mod of Q irrespective of its sign into VB sine theta, where V is the magnitude of the velocity, B is the magnitude of the field, and theta is the angle between the velocity vector and the magnetic field.
So what does the small m stand for? Charge particle Q.
What does the
small m?
Is the mass.
Okay.
That will come into play later when we are discussing about trajectory of a particle and all that. And this is the charge. So typically when we are discussing about the motion of a particle in the field or something, charge is important and its mass is also important, because eventually you want to calculate acceleration. So this FB vector, it stands for magnetic force. Okay, so Now, the next thing which is very important is that the direction of the magnetic force is perpendicular to P and B. That is the nature of cross product. So basically, you can say it is perpendicular to the plane of the two vectors B and B.
Yes.
And of course, if V is collinear, it is theta is 0 or 180 degrees to B, then there is no magnetic force. Or for that matter, V is 0, then there's no magnetic force. So a particle at rest or a particle moving parallel or anti-parallel to the magnetic field will not experience any magnetic force. It must have a velocity which is having some perpendicular component with respect to the magnetic field. Okay, so let's conclude this discussion today with an example. So suppose we have a situation where in a certain xy plane, we have magnetic field lines. We have a uniform magnetic field which is parallel to the x-axis. So later we will understand that this kind of magnetic field, for example, can be produced by a solenoid. If we have a tightly wound solenoid, then in the region which is in the core of the solenoid, okay, so you can just think of the solenoid like a tightly wound coil, okay, like a spring, which has got very tight windings. And if you send current through the coil, it creates almost a uniform kind of magnetic field in the region which is at the core of the solenoid. So this kind of magnetic field typically can be produced like this, that you have a tightly wound solenoid and you're sending some current through it. So you'll see that the magnetic field inside, the magnetic field lines are almost straight like this. It's a uniform magnetic field. So we have a uniform magnetic field of magnitude V naught and direction along the x-axis. Now we have a charged particle which is placed at the origin. This is having charge plus q and mass m. Now it is given an initial velocity like this, some initial velocity u. So we want to find the acceleration vector of the particle is having charge plus q and mass m when projected with initial velocity. Suppose in one case we take it as v naught I cap. Okay. Another case we take it as v naught into 0.6 I cap plus 0.8 J cap. So this is kind of like the one which is shown in the diagram. And in the third case, you have to imagine in the diagram that the initial velocity is not in this plane. So it is, let's say, like this. This kind. So each of these is a unit vector, you can see.
V naught is just a constant.
Yeah, V naught is a constant. So here V naught is obviously a constant. Okay. V naught is a constant. So let's say some numerical values are also given. Magnetic field is expressed in Teslas. We will talk about the unit also later. So you'll see that 1 Tesla is equivalent to 1 Newton per Coulomb meter per second. And that comes from this formula only, that F is equal to QVB. So this unit is force unit divided by charge into velocity. Like this. So let's say this is given to me as some maybe 50 Teslas. This velocity is, let's say, 200 meters per second. Charge is 20 microcoulombs and mass is 1 milligram. So then we can find out the acceleration as a quantity in meters per second square even. Yeah, so to answer your question, Vedant, natural magnets generally don't have uniform magnetic field, especially the bar type of magnets will not have uniform magnetic field. The bar magnet is like this. You must have seen this kind of diagram where you draw the magnetic field lines. There's that classic experiment, no? The iron fillings experiment, where you actually demonstrate the direction of magnetic field lines. It actually looks like the field in the outer region of an electric dipole. However, there is something called a horseshoe magnet that can be used to generate something which is more or less like in a certain small region, the magnetic field generated. So this is the North Pole and this is the South Pole. So there will be sort of slight this thing, but this region will have more or less. So for example, even if you have a coil of current, there will be magnetic field coming out this way also. So the magnetic field in the outer region actually looks very much like that bar magnet's magnetic. But the inside magnetic field actually becomes uniform. So inside this, you have a more or less uniform magnetic field. If this is reasonably tightly wound, okay. Otherwise, even that will not be proper. Okay, so anyway, coming back to this question, you have to just use this formula Q V cross B. In the first case, you can see that the force will be 0, okay, because U cross B will be 0 because they are collinear, they are parallel vectors. But in the second case, the force will have like this. The acceleration will be this force divided by the mass. So in the diagram also you can see that if your B is like this and your B is like this, then what is the direction of V cross B? Is going into the plane. It's into the plane, which we generally show with a cross. You use your right hand thumb rule. So you are seeing actually opposite of what it should be, but I'm pointing my thumb along B and my fingers along B. So it's, for me, it's going into the plane the way I've done it. For you, it's in the other way. Or you can use the cross product method also. Okay. So you can see it will be J cross I, which is minus K. And in the third case, now this is where you have to use the cross product. So when you do the cross product here, you will see. Now this term will give you 0. Then this term will give you again minus k cap. So minus 4/13 k cap. Okay. And this term will give you now k cross I is what, j. So this will give you plus 12/13 j cap. So the magnetic force will have two components now. We'll have a plus y component and a negative k component.
Earlier B vector.
Which one, beta?
B vector is 0, 0.
B vector is along the x-axis, no?
Okay.
So when you do this cross product, no, it is this vector cross with I cap, no, B naught I cap. So I cross I is 0, but j cross I is minus k, and k cross I is j. So that's how we have got this term and this term.
Yes.
Or you can just draw the 3x3 matrix, but it's unnecessary here because it's actually magnetic field only has the x component, not the y and z. So you don't need to draw the 3x3 matrix and carry it. So this kind of thing can also be there in KVPY because it's a bit of application of vector algebra and nothing very complicated. And apart from that, you should know the formula of this Lorentz force and the proper vector formula, not the type of formula you might have seen earlier in class 10 as part of general knowledge, but the proper vector formula with the cross product. Okay, so anyhow, people got quite late, so we'll complete the session here today. Next time we'll discuss more about magnetism, and in that we'll discuss about magnetic field created by a current carrying wire. So that is the source of magnetic field. Today we have seen the effect of magnetic field on a moving charge particle, but we'll also understand what produces a magnetic field, and from there we'll get into electromagnetic induction. So we'll try to look at the essential part of electromagnetism within the next lecture. Yashwardhan, generally speaking, electromagnets are stronger than natural magnets. So obviously a solenoid will be stronger. But to make the solenoid's magnetic field strong, it's not just the coil of current which is important, but at the axis of the solenoid, we have to place a magnetizable material. So that kind of a material is called a ferromagnetic material. So if we place at the axis of the solenoid, like an soft iron core or something like that, which is a ferromagnetic kind of material, then that strengthens the magnetic field a lot. So that's how industrially, for example, electromagnets are created, and those type of magnets generate the strongest fields. Okay, so compared to naturally occurring bar magnets, or when you shape them into horseshoe magnets and all that, electromagnets will have a lot more magnetic field, provided you are sending the right amount of current through. If the current through the electromagnet is very weak, then obviously it produces a weak field. Okay, that's it for today's session. Wish you all the best. Have a nice rest of the night.
Thank you, sir. Good night, sir.
Good night.
Bye, sir. Thank you.
Bye.